Hello, Proviso students, and welcome to Lesson 2.1, Modeling with Expressions. This lesson corresponds with pages 45 through 42 in your workbook. So you want to take out your Integrated Math 1 workbook and turn to those pages, and then we'll get going. Before we begin with the lesson, I just want to share with you that you are in control of this lesson. If you need to pause the video to write something down, you could do that. If you need to rewind the video and watch something, you could do that also. All right, the learning objectives for this section 2.1, Modeling with Expressions, is I will interpret and model algebraic expressions in context. That means you'll be able to write an expression to represent or model a certain situation. That's a context. Or given an expression that models a certain situation, be able to interpret what each part of that expression means. There are some key vocabulary terms that we're going to go over, such as expressions, numerical expressions, and algebraic expressions, terms, coefficients, variables, constants. Many of these terms are defined in your workbook on page 45. We'll go over them right now. When I ask students to represent a scenario with an expression, they usually would think about creating an emoji or identifying emoji to show their emotional expressions. That's not what we're talking about here in mathematics. An expression is a mathematical phrase, or sometimes called statement, that contains operations, numbers, and or variables. Now, operations are the four basic operations we deal with are addition, subtraction, multiplication, division. Numbers are numbers, and variables are unknown quantities that we represent with letters. So what we have here on this slide is 5x plus 3. That is an expression. An expression consists of terms, which the 5x is one term, the 3 is another term. When you have a variable represented by a letter in your expression, then there's going to be a coefficient or a number in front of the variable. Sometimes it's an invisible 1, sometimes it's not. In this problem, the 5 is a coefficient. And then you could also have constants, which are just whole values, or not, I'm sorry, just values, numbers that you're adding or subtracting onto your variable term. So terms of an expression are the parts that are being added. Now, you might have been in the past, you might have worked with expressions where you're adding and subtracting terms. In this particular, what we're doing for this course is we're defining it as the parts that are being added. So if you have, for example, if you have an expression, let's say 3x minus 7, you can rewrite that as 3x plus negative 7. So I have one term here of, my pen will work, 3x, and what am I adding to that 3x? Negative 7. Coefficient is a numerical factor of a variable term. So it is the value that you're multiplying your variable by. So in this case, 5 is the coefficient. X is the variable, and 3 is a constant because that value will not change no matter what the value is for x. There are two types of expressions. One is a numerical expression, and a numerical expression contains just numbers and at least one operation. So all these examples below contain numbers and at least one operation. So 3 plus 2. 3 and 2 are numbers, plus the addition is the operation. 7 times 3, 20 divided by 4. 14 minus 8, 21 minus 5 plus 2, 1000 divided by 8 plus 123. All those expressions just contain numbers and at least one operation. That differs from algebraic expressions. An expression that consists of one or more variables. It could contain some constants and some variables. So the examples we have are 3, here's the first one, 2 times x plus 3 times y plus 6. 2x, 3y, and 6 are the three terms in that expression. Then I could have just 5 times n, a one-term expression. And then I could have, hold on. Let me reset. Too dark. Then I can have just variables terms in my expression. So a minus b, which I would rewrite as a plus negative b. So the terms are a and negative b. One common mistake or error that students have had over the years is that they will, when working with expressions, they will try to solve it like an equation. An expression is not an equation. They are different. Equations have equal signs. Expressions do not. Equations, usually when you get an equation, you must solve for the variable. That's what we ask you to do. So when you have these problems like this, we usually ask you identify the solution, find the value of the unknown that will make the statement true, the equation true. Expressions have no equal signs. You cannot solve them unless you're given the value of the unknown. And when you do that, you're not asked to solve, but you're asked to evaluate. Now, they do have some things in common. What do they have in common? They both have operations. They both have numbers. And they could possibly both have variables. If we're talking about algebraic expressions, then they will have variables. All right, so we have an expression. We have a couple examples of problems that you're going to be asked to do. The first expression we're going to look at is an algebraic expression on the left. We have 4x minus 2y plus 3. First thing I'm going to do is rewrite the expression so that all terms are being added together. Question 1 here asks, what are the three terms in this expression? 4x is one of them. What am I adding to 4x? The negative 2y. And what am I adding to that? The 3. 2. What are the variable terms? Well, they're the terms that have variables that are represented by letters. So 4x, come on, pen, and negative 2y. 3. What is a constant term? That is a term whose value won't change no matter what the values are for x and y, which is 3. We're always adding 3. Doesn't matter if x is 10 and y is 8, or if x is 8 and y is 10. That term is going to be constant. And then we have an extra question there. What are the coefficients? The coefficients are the factors that you're multiplying your variables by. Or, in student speak, they are the numbers in front of the variable. So we have 4 and negative 2. All right, we have a second expression, 5x squared plus x plus 7. Question 4, what are the variables in this expression? What's the unknown? X. 5. What is the 5 in the term 5x squared called? That is the coefficient. 5 is the coefficient of that term. X is a variable in that term. And then question number 6, what is the 2 in the term 5x squared called? That is the exponent. Some people, depending on the context of the question they're responding to, will call it the power. But for our purposes, we're going to say, well, that's the exponent. Now that we went through the basics of the terminology, let's get into some of the problems that are in your workbook. On page 45, on the bottom half, you will see this problem. So what we have are tickets to an amusement park are $60 for adults and $30 for children. If A is the number of adults and C is the number of children, then the cost for A adults and C children is 60A plus 30C. D asks, what are the terms of this expression? So terms are the things that you're adding in the expression. 60A is one term, and the product 30C is the second term. Part E, what are the factors of 60A? Well, factors are the things that you are multiplying together to get a product. So what am I multiplying together? Give me a product of 60A. I'm multiplying 60 and A, if my pen will work. What are the factors of 30C? Well, 30 and C. What are the coefficients of the expressions? Well, the coefficients are the factors is the factor that you are multiplying your variable by. So in this case, I'm multiplying A by 60 and I'm multiplying C by 30. And H, interpret the meaning of the two terms of the expression. So 60A is the total cost of the adults entering or paying to get into the amusement park. And 30C is the cost for the kids going entering, oops, maybe a little issue there. There we go. Entering the amusement park. And the 68 plus 30C gives us a total cost for everyone going to the park, for all adults and all children. The last problem on page 45 is this one dealing with the juices. And the problem states, the price of a case of juice is $15. Fred has a coupon for 20 cents off each bottle in the case. The expression to find the final cost of the case of juice is 15 minus 2/10 times B, wherein B is the number of bottles. Part K. Do both terms have coefficients? Explain. Well, I got 15, and I got that negative 0.2, because I could rewrite this expression as 15 plus negative 2/10 B, if my pen would work. The coefficient is a factor in front of the variable. I only have one variable term. It's at negative 0.2b. So the coefficient is negative 0.2, or negative 2/10. What are coefficients? Coefficients are the factors that you're multiplying variables by. And L, what does the expression 15 minus 0.2b mean in the given situation? Well, they kind of state it in the problem, but what it is for every coupon Fred has, so when Fred has that coupon for 20 cents off a bottle, the total cost, he'll get 20 cents off the bottle, per bottle. That's right there. And that's going to reduce the total cost that you're going to spend. So a more elegant way, I guess, of saying that is, if Fred has a coupon, then 20 cents is subtracted from the price of every bottle in the case. If Fred does not have a coupon, then the case is going to cost 15 cents. So far, we've been examining given equations that model a situation. Sometimes we don't have the given expression, and we have to write the given expression that represents the given situation or the context. Here's an example of what I mean here. Miss Williams has an above-ground swimming pool. When she drains the pool, 22.5 gallons of water will be removed every minute. Miss Williams estimates that there are 3,800 gallons in her pool right now. We want to write an expression that models the amount of water in this pool after m minutes of draining. So we have 3,800 gallons right now, and we're going to drain it. So if we're going to drain it, are we going to add water to the pool or take water away? Well, we're going to take water away. So we're going to subtract how much water. Come on. We're going to take away water. Question is, how much water are we taking away? Well, if we kind of think of it with time in minutes and gallons, then at the beginning we'll have, before we even drain it, or starting to drain it, we have 3,800 gallons. Let's say after 10 minutes. After 10 minutes, then we're going to remove 225 gallons, because each minute we're getting rid of 22.5, so in 10 minutes we'll have a total of 225 minutes gone. In 20 minutes, patience, please. There we go. 20 minutes, I would have 3,800 original, but I would have that amount removed. I would have 22.5 gallons times 20 minutes worth. So the expression would be, there's how many, I'm going to take away that 22.5 gallons for a number of minutes, and whatever the minutes are going to be, that's going to go in there. So my final answer for this expression would be 3,800 original gallons, and I'm going to add negative 22.5 times the number of minutes. That will give me my expression. Many times with writing expression is just identifying what keywords within the problem translate to regarding mathematical operations. You'll see sometimes increase by, more than, combined, altogether, plus, make, added to. All those are keywords that mean addition. Take away, decrease by, minus, difference, less than. Not is less than, that's different. Less than. All those are keywords that mean you have subtraction, times, triple, double, product, multiplied by. Those twice. Those are keywords that mean multiplication. And then per, ratio of, divided by, half, divided into, etc. Those are keywords that mean division. For equals to, is a key word, but you got some of these other words that you will see that also means, hey, I got to put equal sign for that. On page 48 of your workbook, on the top, you'll see a table that have some of the words that were listed on the prior slide. Those words are words you need to be looking for and able to translate into mathematical operations. All right, so let's look at example 3. Example 3 on page 48 asks us to write an algebraic expression to model the given context, give your answer in simplest form. So the price of an item plus 6% sales tax. So what we got going on is, let's just say you go to a store. Let's work with numbers first. A lot of times it's easier to work with numerical expressions before we go to the algebraic expression. So let's say we have $10. Oy, come on, pen. We got $10 that we are of some item that we're going to buy. We go up to the cash register, they put it in, and then they add up. The cash register will automatically calculate the tax and add together. Well, what they're doing is they're finding 6% of your sale price. So what it's doing, it's taking that $10 and multiplying by 6%, or 0.06 as a decimal. And we're adding them together, and that will give us, in the end, $10.60. So let's say now we change that, and we're buying I'm just going to go and write with my finger because my pen's not working well. So $12. And once again, $12 is the original price. I'm going to have to find the 6% at $12 and add it onto my original price. So I'm going to take the original price of 12 and multiply that by 0.06, and you'll get your answer. Let's say you're buying something that's expensive. I don't know, brand new pair of Nike gym shoes, even though it might cost Nike make them $15, they're selling them for $200. And so you go and you buy it, you go up there, person will put 200, cashier will put $200 in the register, and then the register will automatically calculate the sales tax by applying this expression of 200 times 0.06, and whatever that number is, it adds it onto 200, and you get your sale price. The thing is, those are all numeric. Is there a way we could represent this with using variables, one variable expression? Well, let's say P is the price of the original item. Then when you want to find the 6%, you're going to take that P times 0.06. So what we have is 1P, the original price, plus 0.06P, the sales tax, and you end up with 1.06P. And there's your answer. Or there's your expression that represents, that models the context in A. Now let's look at B. We have a car. It has a 8.5% sales tax. So let's say it's a used car, and it costs $5,000. You're gonna buy it. Well, to figure out the sales tax, you're gonna take your original amount of 5,000 and times that by 0.085, and you'll get your answer. Likewise, you have the car. No matter what the price is of the car, to find the sales tax, you're going to take whatever that original price of the car is times 0.085, and there's a visible 1 in front. So if I add those like terms together, I have 1.085 C for car. You can use any variable you want. It could be P, it could be X, doesn't matter. All right. Those two expressions that I've written down and I've circled are the expressions that could be used to figure out the total price of both objects with the sales tax. All you gotta do is put in the original price in for the C or the P, and they'll give you your total price, which is your actual price plus actual sales price plus the sales tax amount. Let's look at one more problem. We will write an algebraic expression to model the given context. Give your answer in simplest form. That means if we could combine like terms, we combine like terms. So the number of gallons in the the number of gallons of gasoline in the car that already has 12 gallons in it as it burns gas at a constant rate of 1.25 gallons per hour for H hours. All right, so we're starting off in the car. We got total 12 gallons. But we're burning gas, so we're taking away the amount of gas in the car. And at what rate are we taking away the gas? Well, it is reducing 1.25 gallons per hour, but we want to know how much gas there will be after H hours. There's our expression. And see how it works. Let's say this is time and this is gas. Right at the beginning, we got 12 gallons. We haven't been driving. In 1 hour, we're getting 12 minus 1.25 of gallons of gas. In 2 hours, we'll have 12 minus 1.25 times 2, because I'm going to burn 1.25 gallons the first hour, and then another 1.25 the second hour. Let's say in 5 hours. I got 12 minus, now I got 5 hours, and each hour I burn 1.25 gallons. So I got 5 groups of 1.25. So I'll figure out how many total gallons that would be. I would just take the 1.25 minus 5. So this table here, table of values, shows how this is working and where this comes from. All right, so these are the notes. We're going to do more of these problems in class, but by watching these notes, you're very prepared and ready to go when we hit class time. All right. You guys have a good day. Take care. Bye-bye.